Ms. Heaton, signing in to talk about empirical formulas. This is in your book, chapter 8.6 through 8.9, if you would like to see this in another format or to see more examples. We're going to be talking about both empirical and molecular formulas today, but let's start with empirical formulas. These are formulas, like we've been talking about, letters representing each element, C, H, and O. And these formulas show the simplest ratio between the elements in a compound. So let's look at some examples / non-examples here. Is this first example empirical? Well, no, it's not, because this could be reduced to CH, because it's a 6:6 ratio, which is the same as a 1:1 ratio. So this is a non-example, but CH would be an example. How about SNO, tin 4 oxide? This would be an example of an empirical formula because it's a 1:2 ratio. That's the simplest ratio between those elements. On the other hand, SN2O4 would not be an example because it could be reduced to SNO2. And how about this one, Ca1.5N1? Obviously, that's not a whole number ratio. Oops, that wasn't in my official definition, but it does need to be a whole number ratio. So this would not be empirical, but you could write this as Ca3N2 and have it be empirical. Well, the goal today is to be able to figure out that empirical formula working backwards from percent composition, which you just watched a different screencast on. And there's a little haiku here. I don't know why that looks so funny. There we go. The haiku for empirical formula. If you remember what a haiku is, there's the first line that's got 5 syllables, the second one has 7, the last one has 5. So you can remember this little poem to help you remember the steps for finding the empirical formula. The first step is to do percentage to mass. Then you convert mass to mole. You divide by small, and you multiply to the whole. This last step you may not have to do. You may already have whole numbers at this step. The examples we're going to work today, I don't believe have anywhere we have to do that last step, but you will get to practice that in class. So let's just dive right in and try an example. A compound is analyzed and found to contain 68.54% carbon, 8.63% hydrogen, and 22.83% oxygen. What is the empirical formula? The first step is to take the percentages of each element that you're given and convert them to masses. So what we can do is assume that you have 100 grams of sample. If you have a 100 gram sample here in our problem, what is 64.54% of 100? Well, it is 68.54 grams of carbon. And it would be 8.63 grams of hydrogen and 22.83 grams of oxygen. It's really just that simple. That's step 1. Step 2, mass to mole. So what we want to do is convert each of these masses to moles so that we can eventually find the mole ratio between them. So what we're going to do is be multiplying by 1 mole over the molar mass of that element from the periodic table. And if you remember, carbon has a molar mass of 12. If you don't, let me just show you here. Oops, that's not the right page. Here we go. Carbon has a mass of about 12 grams per mole. So you'll divide by that molar mass, and 68.54 divided by 12 turns out to be 5.712. And you want to keep a few decimals here because if you round too early, you might end up missing out on the correct answer. So I'd say keep like 3 decimals at this point. Now for hydrogen, we know that 1 mole of hydrogen weighs about 1 gram of hydrogen. So that's going to be easy. That's 8.63. And maybe we should put units on here. Moles of carbon, moles of hydrogen. And then for oxygen, 1 mole of oxygen weighs about 16 grams. Remember that a mole is 6.022 times 10 to the 23rd atoms. So it's just a large number of atoms. And so in moles, we have 1.427 moles of oxygen. Okay, that was step 2. Step 3 says divide by the smallest number. So looking at the numbers of moles that we have, what is the smallest? Because what we want to do is find the lowest whole number ratio between the moles of each element. Looks like oxygen is the smallest, so we'll divide each of these by 1.427. So we can get a whole number ratio between each of our elements. So 5.712 divided by 1.427 turns out to be 4.00. Hopefully we're going to get a whole number at this point. That turns out to be basically a whole number, about 4 carbons. And then for our hydrogens, 8.63 divided by 1.47 turns out to be 6.05. That's about 6 hydrogens. And then for oxygens, obviously that's going to be 1 oxygen. Do we need to do our last step, multiply till whole? No, we do not, because we have basically whole numbers here. Now, this is all experimental data, so you're not going to get exactly whole numbers each time. But if you get something like something 0.0 or something 0.9, you can just round that to the nearest whole number. And so our answer here would be C4H6O1, or just O. This would be the empirical formula, because it's the lowest whole number ratio between the carbons, hydrogens, and oxygens in this compound. Now, let me say a quick note about this multiply till whole piece. What is an example of a number that you would need to multiply? Well, let's say that we also had nitrogens in here, and we ended up with 2.5 nitrogens at this point. Well, in this case, what we would need to do is multiply each of these numbers by some number so that they're all whole numbers. And something and a half, well, if we double it, we know we'll get rid of the half. So then we'd have 8 carbons, 12 hydrogens, 2 oxygens, and 5 nitrogens. But that wasn't the case here, so we won't do that. You'll get to practice that more in the future. Okay. Now there's one other piece I need to talk to you about, and that is molecular formulas. These tell the actual number of each atom in the molecule. So it's not the lowest, simplest ratio, but it's actually how many are in that molecule. So if you were building with the model kit exactly what it looked like, you would have to put that many of each atom in there. So an example of a molecular formula is C2H4, because an empirical formula for that could be reduced to CH2. This is always going to be some multiple of the empirical formula. And you can think of this as a formal, process, a formula, but you're going to see that it's pretty easy to come up with this. Basically, what you want to do is figure out how much heavier the molecule is than the empirical formula's molar mass. So what you'll do is you'll find the molar mass of the empirical formula, take the molecular weight that the molecule is known to weigh, and find the ratio between those two. And it should be some number, like 2, 3, or 4. Then you're going to take that empirical formula that you found earlier and multiply it by whatever the ratio was to end up with a molecular formula. So let's say that we had CH2. We knew that was the empirical formula, and we knew that the molecule was twice as big as the empirical formula. You would just double each of those subscripts, so it would be C2H4. Let's try that. If we knew that the empirical formula was C4H6O, I'm going to write that down here, C4H6O, that's our empirical formula. Find the molecular formula if the molecular weight is known to be 140 grams per mole. So what we need to do is figure out the molar mass of that empirical formula. So using the periodic table, there are 4 carbons and 6 hydrogens and 1 oxygen. So when you calculate that, that turns out to be 70 grams per mole. So our empirical formula would weigh 70 grams per mole. But it looks like our molecule is 140 grams per mole for its molar mass. So you can probably see that the molecule is twice as big. If not, you could think of this as finding the multiplier by doing the molecular weight, 140, also known as the molecular mass, and dividing it by the empirical formula's mass. And that turns out to be 2, which means that our molecule is twice as big as our empirical formula. So we'll take our empirical formula, C4H6O, and double all of it to get C8H12O2. And that would be our molecular formula. Okay, folks, here's a practice problem for you. Take a minute to read this problem and work out the answer. You have isolated a compound and set it in for analysis to help determine its identity. So let's see if you can find the empirical formula and the molecular formula. So hit the pause button until you've done that. And then take a minute to check your answers. Here's what you should get. Okay, if you've got questions about this, please bring it to class and talk to your teacher about it tomorrow. Happy formulating!